Three, two, one. Welcome to another 2070 online video. Alright, so as promised, in the previous video today, we are going to talk about inverting matrix multiplication, specifically the inverse of a matrix. Alright, so last time we talked about matrix multiplication, and one of the things we pointed out is that it has an identity, which allows us to meaningfully talk about inverting, in the sense that I am going to have an inverse of a matrix if I can find a matrix so that multiplying on the left and the right will give me the identity. Right, so very similar to how 1 over a matrix should be defined, right? We have a 1 for matrix multiplication, the identity matrix. So 1 over it should be something that satisfies these algebraic equations. Alright, it takes a little work, but you can prove such a B is unique, and the notation we use is a to the negative 1. Not shocking there. Let's immediately jump in and talk about probably one of the most absolute famous matrix facts of all time, which is that 2x2 matrices have a very nice formula and check for being invertible. A 2x2 matrix, represented here as A, B, C, D, is invertible precisely when this magic number, the product of the diagonal minus the product of the off-diagonal, is non-zero. And we arrive at probably one of the most important formulas we're going to see in this class, the inverse formula for the 2x2. So in your mind palace, where you've got the formula for the quadratic equation, negative b plus or minus the square root of b squared minus 4ac all over 2a, go ahead and put this right next to it, because this is just as important. I promise you, you are going to use this formula at some point in your life, and it will be outside of this class. It will happen. It has happened to me. It will happen to you. So, I can't understate how this formula sneaks its way into your life one way or the other. It's going to, in 20 years, it'll happen to you, and you email me and be like, I did it, you told me, and I didn't believe you, but then it happened. Alright, so that being said, let's see it in action. So we have a formula that detects invertibility and gives me a formula for it. So if I take a 2x2 matrix here, 1, 2, 1, 2, the magic number is 0, so this does not have an inverse. I cannot find a matrix B, so that A times B and B times A is the identity for this matrix right here. And suspiciously, the rows are the same, and the columns are scalar multiples of each other, like almost they're not linearly independent. Alright, but here, note a ever so slight modification of the matrix, turn this 2 into a 3. Magically now it is invertible, and we have a pretty nice formula for the inverse, since the magic number ends up being 1. Alright, sweet. So for 2x2 matrices, we have this very wonderful formula for invertibility and a good check for invertibility. Now is a good time to ask, alright, well, I can do this for 2x2s. Why do I really care about doing this? Alright, well, right off the bat, there's some quick formulas for inversion in matrices that are important to point out. Inverting the inverse gets you back to normal. That's not shocking. 1 over something gets us back to where we started. A product is invertible, and the order of the inverses reverses. That is best seen by taking A times B and multiplying it by B inverse times A inverse. B times B inverse gives us the identity in A times A inverse. And we know that matrix multiplication is not commutative, so in order for the multiplication to get you the identity, you have to reverse the order of it. And transposing does not mess with invertibility. The inverse of a transpose is the transpose of the inverse. Again, our favorite phrase in mathematics, the x of the y is the y of the x. So those ones aren't too shocking, and these formulas will pop in and out throughout the semester. We don't need to get too crazy about these right now. But the real money, before we get to the real money, we actually need this one a little bit. The middle one is actually kind of interesting because you can do this to multiple matrix multiplications, and you just got to reverse the order. So, for example, the inverse of A times B times C is exactly what you think it should be, just flip the order. Alright, now let's get to what I actually wanted to talk about. I forgot. We're going to need this in a second. But if you have an invertible matrix, then the real power here is that this has exactly one solution. What you've been wanting to do to this equation, you can finally do. You can divide, with massive quotes around that, the A to the other side. And there we go. You have exactly one solution. It is A inverse times B. Right, and this is found by just multiplying both sides by A inverse. A inverse times A is the identity. The identity times X gives me X. Boom, we're good. Alright, so that means if you have an invertible matrix, then I can solve Ax equals B exactly. It has a unique solution. And oh boy, we've already seen that the exactly unique solution kind of only happens when the columns are linearly independent. All right. So for an example of this in action, set up the following system. Turn it into a matrix equation, find the inverse of the matrix, then we get our unique solution. This inverse times this vector, there you go. Right, here we see the inverse, of course, no guarantee that these do look nice. Note you are going to have to do 1 over something that you scale. So, and our example, of course, had the scalar equaling 1, but it's possible you've got, less fun scalars. Here, in this case, 7. But hey, there you go. I can now solve ax equals b if I know a is invertible. But of course, now this begs the question of, all right, well, this worked out great for a 2x2. What happens if I got a 3x3, or a 4x4, or a 5x5, or a 10,000 by 10,000? Well, what do I do then? The 2x2 had a nice little formula. And when I was first learning this stuff, I was learning this in my pre-calculus class in high school. My professor, my teacher for that class, Mr. Como, somebody asked, hey, is there a formula for the inverse of a 3x3? And he outright said no. And I disagreed. And I spent the next day coming up with the formula for it, and I got it. And I was very proud. And I was like, I'm going to prove you wrong. But then he's like, well, yeah, there is a formula, but look at what you got. Is that useful? And I was like, well, no, but there is one. Now, there are formulas, and later in the course, we will actually talk about the actual formula. We'll talk about the adjugate matrix, which is the formula that you can get for it if you want it, and as you'll see, it's not exactly great. But it turns out we do have a nice algorithmic way of generating the inverse and checking for invertibility using row operations. All right. So the first thing we'll note is something that we kind of already know has to be true, is that any invertible matrix has to be row equivalent to the identity. And this just has to happen for a variety of reasons, but since we know AX equals B as a unique solution for any choice of B, if we then look at our augmented matrix, and if we were to get it in reduced echelon form, you have to get the identity matrix on the left. If anything else, so for example, if there is a row of zeros in the bottom row, well, then there's a B you can choose to get an inconsistent system. But we know the system is always consistent, any choice of right-hand side. So this can only ever ref to the identity matrix. It can't ref to anything else. Otherwise, you're going to have either an inconsistent system or infinitely many answers, both of which we know can't happen. All right, so if you're invertible, you are row equivalent to the identity. What about the flip? Let's say we know we're row equivalent to the identity. Does that mean you have to be invertible? The answer is yes, as always, but why? So it turns out that there is a special type of matrix that's worth discussing, and that's the elementary matrix, which is a matrix that you obtain by doing a single row operation to the identity matrix. So, for example, this right here is taking the first row, scaling it by -7, and adding it to the second, applied to the identity matrix. Whereas this matrix, there's no way to obtain this by one single row operation applied to the identity. Now, the real power of these elementary matrices is that multiplying by one of them is the same thing as performing the row operation. So, for example, here I see the elementary matrix found by scaling row 1 by -7, and if I were to multiply this matrix by it, we see that, oh hey, it scales row 1 by -7. So that means row operations are really just matrix multiplications in disguise. So that's really powerful, because that tells me that every elementary matrix note has to be invertible, because its inverse is given by the elementary matrix of the same type, specifically the row operation under whatever you did. So if you were to scale by -7, then scaling by -1/7 will get us back to the identity. If you were to swap two rows, then swap the rows again, you're back to the original matrix. And scaling and adding a row will scale and add to make the 0. And in particular, this is a fun one. Here we see the identity matrix after swapping rows 2 and 3. This is an elementary matrix, and it's its own inverse, because multiplying by it will swap rows 2 and 3, and that'll get me back to normal. So here we see that row operations are actually matrix multiplications in disguise. That's pretty cool. And with this knowledge now, if we were to follow the thread, if we have a matrix that is row equivalent to the identity, that means that I can multiply it on the left by enough elementary matrices to get us to the identity, just perform the row operations that get you to the identity matrix, Each one of these is invertible, which means I can multiply both sides by their inverse, and note it'll then swap them in reverse order. Note that A has to now be an invertible matrix because it's a product of invertible things. And in fact, this tells us that every invertible matrix is in fact a product of elementary matrices. So another way of thinking about elementary matrices is like they're kind of the prime numbers, right? Every positive integer can be written as a product of primes. Here we see every invertible matrix can be written as a product of elementary matrices. Pretty neat. And now the money here is this actually gives us the method for producing the inverse of a matrix, because here we see that if I take a matrix and I apply these row operations, I'm multiplying by an elementary matrix, and that gets me to the identity. The matrix A itself has to be the product of the inverses of these, so if I were to replace A with A inverse, so if I want to actually produce the inverse of a matrix, we set up a matrix where we have the matrix A on the left and the identity matrix on the right. We then perform all of the row operations that turn A into the identity matrix on the left, and all of the row operations on I here being applied are going to then turn I into some matrix. That matrix that it turns it into has to be A inverse, because we're using all of the row, we're doing all of the, we're applying all of the row operations on A that get us to the identity, and as we see right here, that's precisely what A inverse is in this formula. Neat. All right, so we now actually have an algorithmic way of producing the inverse of a matrix, and also detecting if we have an invertible matrix or not. We'll see that in action here in a second. All right, so you simply set this up and do your row ops, and obviously for a 2x2, you don't want to do this because we have a nice, clean, simple formula for it, but for 3x3 and beyond, this is what you want to do. So, for example, if I were having the matrix 1, 0, -2, -3, 1, 4, 2, -3, 4, I slap the identity matrix on the left, I perform my row operations to get the identity matrix on the left. I now know that this matrix is invertible, and I have a formula for its inverse here on the right. Ta-da! And absolutely this is going to be a problem on a problem list, so get ready to perform this. Alright, and as promised, and the final point, this method will also detect if you are invertible or not. So for example, if I look at my favorite matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, we've already seen the ref of this, and we know the ref of this gives us a big fat row of zeros. We can perform the row operations, but on the right here we'll get something, but on the left we note that we are not a row equivalent to the identity, because I got a big fat row of zeros. So we know that that means that we can't possibly be invertible, because as we've already established, a matrix is invertible precisely if it's row equivalent to the identity matrix. Every invertible matrix is row equivalent to the identity, and if you are row equivalent to the identity, then you have to be invertible. So here we see that a pretty innocuous looking matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, you feel like this should be invertible, right? All I did was just populate it with integers in order. Why did it not work? Was I populated with integers in order, and note here that adding 1 to the first column gets me the second, and adding 2 gets me the third column. Adding 1 to the column gives me the second, adding 2 gives me the third. Oh, like there's a linear combination that connects all of them. Ooh. So it turns out that if you actually populate your matrix with your integers in order for 3x3 and 4x4, 5x5, and beyond, all of those end up not being invertible because they're row equivalent. Because there's a linear combination for the columns, which guarantees the columns aren't linearly independent, so they can't be invertible, as I've already let slip. But note, the 2x2 case does work. 1, 2, 3, 1, 2, 3, 4 is actually, in fact, invertible, and it's because you don't have 3 or more columns. Right, remember, the linear independence is a weird thing that happens. There's a subtle change when you jump from 2 to 3. Right, because in the 2 case, you just need scalar multiples, but for 3 and beyond, you need that linear combo. And here, this gives you sort of like why that ends up happening and the subtleness of it all. But alright, cool. Alright, so there we go. We have now seen how to invert matrix multiplication, and we know why we want it. We want it for a very specific reason. It helps us solve systems. Good stuff. Alright. I will see you in the next video.